4.2 RSG. This homework is very similar to 4.1, so it shouldn't take as long to go over it. But who knows? Let's see how it goes. So when I'm looking at the ready, I see more fractions, and you're all probably groaning right now, complaining that, oh my gosh, I hate fractions. I don't want to do this. Fractions are our friends. They're not that bad. If you can work with fractions, you could do anything. So have confidence. You know how to do this. When we are adding and subtracting, what must we have before we can add or subtract fractions? We need a common denominator, which is, I know all of you are saying that right now. When I look at 2 and 3, my common denominator is 6. I don't even bother with getting a least common denominator when I do these. Just get a common denominator. In order for 2 to become a 6, you have to multiply by 3, which means you have to multiply the left side, the left fraction, 1/2 by 3 over 3. You're not changing the number. You're just rewriting it. In order to turn 3 into a 6, you must multiply by 2. So you have to multiply by 2 over 2, so it's still 1. So I now have, well, you guys can finish that. That's all I'm going to do there. So you would multiply, actually maybe I should, because it'll help you with 4 and 6. When you multiply fractions, you need to remember that you multiply straight across. So this new fraction will end up being 3 over 6 plus 2 over 6, which becomes 5 over 6. So you're going to do that same thing in 4 and 6 where you just multiply across. Be careful in 2 that you do need to subtract. And then in 5, because it's division, you need to make sure you take the reciprocal of the second number. So it's 1/6, and when we divide it by 2/5, we multiply by 5/2. We're increasing that number instead of making it smaller because we're dividing it into a bunch of smaller pieces, which will give us more. And then multiply across. And then just think about 7 and 8, 9. What is that process? Like for subtracting and adding, what is the process? You have to have a common denominator, and then you add the numerators, but you do not add the denominators. Things like that. And then do the same thing for multiplying, and then the same thing for dividing. It will make 4.3's work so much easier. Okay, now let's look at the set. The set is finding roots and domains of each of these functions. Now I want to draw your attention to 10, 11, 14, and 15. Those should look familiar. In module 3, we saw functions like that. And what do we call these functions? These are our polynomial functions. And we need to remember from polynomial functions that they are continuous. And if you look at your foldable, you have that definition. And you should also have how to find the roots of polynomials and how to find the domain of polynomials. Relatively easy. Now I'm going to do 10 with you because it's already factored. I don't want to take away your practice of factoring. It is important that you guys are able to factor. So to find my roots, you have to have your factors, and your factors, you set each of those equal to 0, and you get your factors. So this factor is negative, or this factor gives us -5, 0. This factor gives us 2, 0, and then 7, 0. There's my roots. Now I need to find my domain. When I am remembering polynomials as being continuous, I can go from the left to the right, and that graph just keeps going and going and going, which makes our domain all reals, -infinity to infinity. That should help you with 11, 14, and 15. Now, 12 and 13. are your rational functions. In class, we have gone over roots. Roots are the x-intercepts. To find the x-intercepts, I'm not going to do 12, but I'm going to do 13 with you. To find your roots, which are your x-intercepts, we make y equal to 0. So if I make y equal to 0, I get negative x plus 2 over x plus 1, x plus 5. We did go over this in class, but just in case you need it again. I have a fraction. I don't want a fraction, so I multiply by the denominator. And when I multiply by the denominator, I have to multiply both sides by the denominator. Well, it's going to cancel here on the right side. And then when I multiply x plus 1 and x plus 5 by 0, I get 0. So I am left with 0 equals negative x plus 2. So I move the x over and x equals 2. So I have one root at 2, 0. In class, we talked about your roots. Easy way, knowing that this will become 0, you are looking at just the numerator. It'll make everything a lot easier if you remember your root comes from, for only rational functions, your root comes from the numerator. Now, the domain. With rational functions, we need to remember that there are asymptotes involved. And again, we talked about this in class. Your asymptotes are the undefined values. What puts a 0 in the denominator? So for my domain, I need to look at the denominator. So my denominator is x plus 1 and x plus 5. What would make this 0? Oh, if x were to equal negative 1, that's 0. What makes this number 0? A negative 5. So it's just like you're solving for roots. Same thing, but we're looking at the denominator. So these are the values that make the denominator 0. If I plug in negative 1 plus 1 is 0, which makes the whole thing 0. If I plug in negative 5 plus 5 is 0, which makes the whole denominator 0. So when I'm writing my domain, I'm going to use set notation. X such that x cannot equal negative 1. Actually, I should put negative 5 first, the smaller number first. Negative 5 and negative 1. Recognize that these two numbers are also your vertical asymptotes. They come from the denominator. So domain, vertical asymptotes, they go together. I hope that helps. We're going to continue to see this. This is just building a foundation right now. We're going to practice this some more. So if you're still kind of feeling like, oh my gosh, I'm not getting this, it's okay. We're still working through this. This is still early in the module. It will come. It's going to happen. Just keep plugging along, keep trying, keep doing your work. Now the go. Wait a second. These look like the same ones back here. The only one that's different is number 12. And it says I need to solve them. Same equations. Oh, wait a second. They're not equations. They're inequalities. So close. But you've done the work back here in the set. So let's see. I think with you guys, I'm going to just briefly discuss a couple of these. I will completely do 13 with you because it's another rational function and it's new. Maybe get you started on 10 and show you how easy 12 is going to be. I'm not doing the ones that need to be factored. You guys can do that. So if we remember from the set, here x was -5, 2, and 7. Make a number line and test numbers. Here's -5, here's 2, here's 7. Because these are equal to, it's greater than or equal to, close circles. Now you need to test numbers. And I'm not going to do all of the testing here because I'm going to save it for 13. You would probably want to test something like, well, -6 or less. Something in between -5 and 2. So how about 0? Something in between 2 and 7. Let's go with 3. Something greater than 7. Let's go with 8. So you're going to take those numbers and you're going to plug them in. Plug them into your original inequality and see if they're greater than or equal to 0. Remember, if it's yes, you highlight that section, and then when you're done testing all of them, write your intervals. You will need to do that for 10, 11, 14, and 15. 12 is different. How is 12 different than any of these other ones? When I look at 12, I just see one x. I don't see exponents other than the one that's there. It's just very straightforward. 3x minus 5 is greater than 2. Well, that's nice. You can actually just solve this one. So 3x is greater than 7. There's no guessing here. It's just one variable. Divide by 3, and x is greater than 7/3. You don't even need to test. That is your solution. And I would leave that one as a solution set. So x such that, sorry, I can't draw the swigglies. X such that x is greater than 7/3. Now let's do 13. This is the last one that I'm going to do for you in the video. This is going to take us some time. When we're solving, we're looking for the x-intercepts. So if I take my numerator, -x plus 2 equals 0, like we did before, and what did we get back in the set? We got, my mouse keeps moving. We got +2. Then we also have to look at the denominator. And I thought I changed the color. The denominator is different. These are what they cannot equal. X cannot equal -1 and -5. So when I make my number line for testing, I'm going to put the -1 after the -5 and the 2. Because, now listen carefully. Please listen. And if you have to rewind it and listen to it again. The -1 and the -5, x cannot equal those two numbers. Those are your asymptotes. So I'm going to put open circles because they are my vertical asymptotes. X cannot equal those, but they are boundaries in my graph. You could have something in the middle of them. You can have something on the outside of them. You have to put open circles there. Now on the 2, for the 2, you look at the original inequality. And the original inequality is greater than or equal to. The 2 gets a closed circle. Please be very, very careful there. So now I'm going to test. And I'm going to test -6, -2, 0, and 3. And I'm going to plug back into the original. So let me erase that so I can see it. So -6 plus 2, -6 plus 1, -6 plus 5. And I'm checking to see if they are greater than or equal to 0. So here, I'm going to do one at a time this time. There we go. I had the parentheses wrong. -6 is 6 plus 2. This is going to be -5 and -1. So this is going to be 8 over 5. Is that greater than or equal to 0? Yes, because it's positive. So I'm going to highlight that section there. Okay, now I'm going to plug in -2. -2 plus 2, -2 plus 1, -2 plus 5. So let's see, this is going to be 2 plus 2, -1, and 3. So this is going to be 4 over -3. Is that greater than or equal to 0? No. So I do not highlight that area. Now I'm going to plug in 0. -0 plus 2, 0 plus 1, 0 plus 5. I get 2, 1, and a 5, which is 2/5. Is that greater than or equal to 0? Yes. So I'm going to highlight here. And now I'm going to try 3. -3 plus 2, -3 plus 1, -3 plus 5. So let's see what this gives us. -1 for the numerator, -2, and we get +2, which gives us -1 over -4. Is that greater than or equal to 0? Yes, because I have two negatives that are going to end up going away. Oh, I made a mistake. I'm sorry. I am tired, you guys, and I am sorry. This is +3 plus 1. Some of you are probably getting really frustrated because you probably wrote all that down, and I'm sorry. This is -1 and 4 and 8. This is -1 over 32. Is that greater than or equal to 0? No. Okay, now I just need to write my solutions based off of my number line. So my solutions, I'm going to use interval notation. This first piece here, where is that going? -infinity. What is it coming up to? -5. So -infinity, ugly infinity, -infinity to -5, not included because it's an asymptote. Union, I jump all the way to -1, not included because it's an asymptote. And where does it stop? At 2, which is included because it's greater than or equal to. For set notation, this would be x is less than 5 and greater than -1, less than or equal to 2. You take your pick how you want to write it. I will be prepared for either one when you guys are writing your solutions on any assessments. All right, that wraps up the video for 4.2 RSG. Questions, write them down. Make sure you are checking your answers, please. And coming in and see me morning, lunch, after school for anything you need help with, or when we have our homework question day, please make sure you ask if you can wait. If you can't, come in and see me.